Okay, so now let's summarize what we've found out in this experiment, okay? So we've kind of already done all of the sample sizes. So we're going to look at the parent population, so what the original population looked like, the different shapes, and the samples we took, and kind of what the distribution of the random samples looks like. So we did several different shapes here. We started with skewed. So I'm going to kind of write these along the top and make a little table here. Then we looked at uniform. Then we did the bathtub / custom, any shape you want. And then we looked at normal. Okay, so for skewed we did n equals 2 and 5. And that was still skewed, right? But maybe got a little less skewed over time. And then when we averaged 25 together using the simulator, it came out normal. Okay, I'll switch colors here. With the uniform, we did n equals 2 and 5. We did the small ones and then actually also 25. And that looked pretty normal the whole way because it's symmetric. The bathtub or custom, first we did n equals 5. And that was not normal. But when we did n equals 25, it looked pretty normal, like a normal distribution. And then when we started with a normal distribution, we did n equals 2 or more, because even at 2 it was a normal distribution, and so anything above that is going to be normal. Now there are some differences, we'll get to that in just a second. But really, as long as we were at the 25, everything was looking like a normal distribution. And then the normal, starting normal, is always going to be normal. Okay, so let's go back to these windows for a second here. Look at the statistics posted on the left side of each window. For each one, exactly does the mean refer to? And why do they differ? So let me click on my simulation again. So here we have, the first one is the parent population. So for the parent population window, that's the mean of our population. So parent our mean, we would call that mu. That's we use the Greek letter because it's referring to our population. So this is called our population mean. We're going to give this some notation here because it gets confusing when you're talking about the mean of the means. Then in our other window down below, our distribution of the means, we have 2 of these depending on the sample size. That one is the mean of our random samples. So let me go back to the notes here. So in our distribution, I'll say distribution of random samples, because that helps make it more concrete. Our mean there, we could call it mu sub x bar. So our x bar referring to a sample mean, and then the average of the sample means, right? So this is where it gets a little dicey sometimes. So this is the average of the averages of the random samples. So we have the mean of the means here. So you'll see us writing down 2 different means because we have the original mean and then we have the mean of the distribution of the random samples. Okay, Now let's write a little bit more here on what we did. So let's write about the normal thing that we actually did last. If we start with a normal distribution, then the shape really didn't change, right? The shape stayed normal for any sample size. But what changed? We had, well, actually, the mean actually stayed the same. We had the same mean. But what changed was the standard deviation. We have a smaller standard deviation. And we could even say as n goes up, the standard deviation goes down, right? The larger sample you have, the smaller the standard deviation will be. Okay, and then now let's kind of summarize if it was skewed or other. If we start with a skewed or other population, the sample, or sorry, let's write the distribution of random samples looks normal after a sample size of 25. Okay, so as long as we sample large enough, we will get to a normal distribution. And then this had the same mean as the population and also a smaller standard deviation. And the same pattern, as n goes up, the standard deviation, I'll abbreviate, goes down. The more we average, the closer the average is going to get to the mean, because you'll have some on the right, some on the left. They're essentially going to bring each other in to the mean. Okay, so what we just discovered is called the central limit theorem. Now, I don't know if you realize the power of this. This is really amazing, because what this means is we don't need to know our original population. And that's really good, because we don't know. We usually don't know what our population shape is, right? We're trying to take samples to understand what our population, something about our population, but we might not even know the shape. So the reason this is so powerful is that we don't have to know the shape, because as long as we sample enough, it's going to be normal. And then we have our handy-dandy probability calculators to where we can calculate what we need to. Okay, so it's very convenient and brilliant that this works out this way. Okay, so this is called the central limit theorem. Let's go over what this says, and then we'll do some examples in the next video. Okay, so what this is saying is the mean of a random sample, it's a random variable, it's a variable like we've been studying, whose distribution can be approximated by a normal model. The larger the sample, the better the approximation will be. So the distribution essentially becomes normal the larger the sample you have, okay? And it doesn't have to get too big, right? But we do have some conditions, and think about the drawing, the original drawings that we did, okay? The first assumption is that the people in the sample were independent of each other. So because we're drawing random samples, we need them to be independent. So do you think that people in a stats class, the number of piercings they have, would those be independent from each other? Probably, unless their piercing buddy was in the class with them and they got a lot of piercings together. They probably would be independent of each other. So independence is important. And the other thing we need for independence is the 10% condition. So remember, the other thing we've studied is how we can't sample more than 10% because we're sampling without replacement. So as long as we sample less than 10% of the population, then we can also assume independence. So we'll talk about that more when we do some examples. Okay, so independence is the first condition with the 10%, and then the second one is randomization. Now these samples were randomly chosen, right? And that it was really important to get that average to come out the way it did. So the samples need to be randomly chosen, and that also kind of goes along with independence. If they're not randomly chosen, we don't really have independence. And then the third is the sample size condition, and that's what we were just talking about here. So a normal model is appropriate if the sample is large enough. Now this can be a little vague, so remember it depends on what population you're starting with. What our textbook uses, different books use different numbers. Ours actually uses 30. So we saw 25 looked pretty good, right? Our textbook actually says if you don't start with normal, if you don't start with a normal population, then you need n equals 30. If population not normal. Okay. Otherwise, if the population is normal, then you don't really have a sample size condition. You can use any sample size. Well, that's just barely above my window. We can use any sample size. Okay. So these conditions are really important because in statistics we use a lot of models, and the model is only as good as it fits the situation. So if you're taking some convenient sample and so you don't really have independence, your results really aren't going to be very good, right? So part of statistical thinking is what different assumptions or conditions go along with a model, and how can we make sure that those are met in our situation. Okay, so you're probably wondering, what are we going to do with all this? So I'll show you an example of what we're actually going to calculate and how we can do these problems in the next video. So I'll see you there.